now we have methane, which is also, it's a simple fuel, but it's also a greenhouse gas. So are there synthetic routes from methane to other technologies or to other chemicals? And
well,
what role would this play?
we go CO2 to go to methanol, okay? And the methanol is from the first reaction I said you go from CO2 to methanol. The methanol also is another very important molecule, which is we have a process called methanol to olefins, MTO, okay? And this reactions has to be done on a catalyst which has some acidity. So the acid catalyst like a zeolite. Okay, so the zeolite is capable to the peroxide acid side from this H+, which is ions, which attack the methanol and dehydrate the methanol into dimethyl ether. And this we keep going with the temperature, and the second acid attack will go from dimethyl ether to olefin and other products. In this case, we have to characterize the acidity of the sample. We dose the sample with ammonia, known amount of ammonia, and the system is capable to do pulse chemisorption of ammonia until we get peaks in the same area. We say the sample has been saturated, and the amount of ammonia, total amount absorbed, is equivalent to the acidity of the sample. But for us in catalysis, not only important the total acidity of the sample, but the acid side, which are really reliable and existing at the reaction condition. So in this case, we saturate the sample with ammonia and we do desorption at temperature programs. So we program the temperature to go up from room temperature after saturation, and we can see how the ammonia dissolves from the sample as a function of temperature. And therefore, we can quantify the amount of acid side available for the reaction at the reaction condition. Okay, so by this we can quantify the amount of acid side at the reaction temperature. But also we have another option where we can saturate the sample and desorb it at different ramping rate. Okay, for example, say 2, 4, 5, 6, whatever you like, degree per minute, you ramp it, and then you have a shift on the maximum of the peak. And that shift on the maximum, the peak, as a function of ramping temperature, we can calculate the heat of absorption. Okay, and the heat of absorption gives us very good information about how strong or how weak the ammonia is going to absorb, and how strong or weak the strength of active acid side. So we'll have total acidity, we have distribution of acid side, quantifying the acid side at the reaction condition, and the strength of acid side, which is very important. So if the acid side is very, very strong, the first product is going to stick to the acid side, will not dissolve, and deactivate the catalyst. If it's very weak, means that it's not going to work at the reaction temperature. So we have to quantify from all the activity, all the acidity of the sample, how many acid side we have at the available for the reaction as a reaction condition.